the PIT, the power available on the turbine shaft. And how can you represent the problem? This is very often represented like this. I show you here the thrust. And the thrust in function of the temperature, which temperature? This is the temperature of the gases. This is the temperature of the gases. So let's say the TIT. This is a curve that is something like this. Okay? If you increase the TIT, you increase the thrust. But the situation is that you can have two different limits on this TIT. If you are using, let's say, an uncooled engine, you will be able to go to, let's say, 1000, in order to take an easy number, 1000 Celsius, to take an easy number. And that is delivering you a certain thrust. Let's say 100%, whatever this value is. 1 kilonewton, 10 kilonewton, 100 kilonewton, whatever. What do I try to do? What do I try to do? I'm trying to increase the TIT. I can increase it with the materials. I'm exaggerating, of course. And with the material, you will not go to 1000, you will go to 1050, and instead of 1050, instead of 1000 delivering 100%, with 150 degrees Celsius, you will reach, I don't know, 103%, for example. Or you can use a totally different technology that is enabling a larger increase of the TIT, a larger increase of the TIT thanks to cooling. I'm showing that with a blue color because this is with cooling. And with this, I'm able to go maybe to 1500 Celsius. So not 50 Celsius more, but 500 Celsius more. And of course, in this case, I would be able to reach, let's say, 120%, for example. I take an easy value. But the situation is not like this. What I've made is totally wrong. It's totally wrong because when I'm going to this temperature, using cooling, I have a cooling air. And so this cooling air means that it's not this curve that I need to do, but this is a curve that is parallel to this one, and that can change depending on the amount of cooling air I'm using. If I'm using a lot of cooling air, I will move to this curve. If I'm using a small amount of cooling air, I will move to this curve. And you see that if I'm using a small amount, maybe I will be here at 115%. If I'm using a lot of cooling air, I'm going into this position, which is 103%. If I would even use more cooling air, I would even arrive here that is only at 90%. So you see that the technology is important, but also you may use the technology, not to increase TG, not to decrease TM, but maybe you will use the technology to reduce m.k. You see, m.k is in fact and a parameter and a performance of the situation, because m.k can be decreased by increasing HK/LK, by decreasing LG and G, keeping TG constant, keeping TM constant, but decreasing that, and you will move from this curve to this curve, and you see that without increasing TG, maybe you will, in fact, influence positively the thrust, and of course, also the TSFC. I hope that you have understood this curve. This is a very important curve showing the tremendous effect that you have on m.k. Okay? And so you see, like this, that we have discussed the technology. This is HKLK. Second technology, this is HG, with the film cooling. Third parameter that we have discussed, this is the pressure that is somewhere related to that. I will maybe, if I think about that, introduce you another technique that can decouple the pressure and the temperature. We have discussed this. We have not yet discussed the CPK. CPK, this is using air in aircraft engines. So CPK, you see, if we want to decrease m.k, CPK must be as high as possible. How can you increase CPK when you are speaking of cooling air? It's difficult, because Cp is increasing with the temperature, and we want to decrease the temperature of the cooling air. But there are ways to increase CPK. This is, for example, by using water vapor. Of course, in an aircraft engine, you don't have water vapor, but it would be good to cool down the blade, not with air, but with water vapor. That has a much higher CPK. When can you have something like this? In industrial gas turbines. In industrial gas turbines, where you have also a steam turbine, very often in the cycle, you take cold steam, you inject it there, and you increase the CPK. Very positive for your problem. As I said a few minutes ago, what you could also do, I said TKH is proportional with the place where you take the air, so it's proportional with the pressure of this air. We could decouple the pressure of the air with the temperature Tk up. How could you do that? By putting a heat exchanger. If you put here a heat exchanger, so with the Tk coming from the stage, and you have a flow, let's say, going into the other direction that is cold, a flow that is colder than this, then you see that you can decrease the Tk up. What can be a cold flow that could be available for that? This is m dot secondary. M dot secondary is cold. But this is, of course, difficult to put a heat exchanger, of course, not in the blade. It must be outside of the blade, but this is difficult to put this somewhere inside the engine. You see also that the technique is very complex. The technique is very complex, so it shows, of course, a huge advantage, but the technique is very complex. Why? Because this is air coming from the compressor. So you must take air from the compressor, and it must go to the turbine. If you take a drawing of a real engine like this one, so if you take a real engine like this, it's not this one. If you take a real engine like this one, so you need to bring this air here in the high pressure turbine. But this is coming from the compressor. Or are you going from there to there? Not easy. Very difficult. You need to go along the shaft. So there is little space to put this passage for the cooling air from the compressor to the turbine, especially for the blades, the rotating blades. Because the rotating blades, you need absolutely to bring the air from the root. Whereas in a stator, you can bring the air from the hub also. You can bring from the root and from the hub. So it's easier in a stator to cool down a stator than to cool down a rotor, certainly. Okay? And let's move to a few equations. We like equations as engineers, so let's move to some equations. So the equations are developed in the notes. You can look at the equations, and what is the most common equation that is used when you speak about cooling? This is an equation showing this: Tg minus Tm in function of Tm or Tg minus Tk. Okay? Tk and the specific value of Tk is of course a Tk hub. So, and you will have factors that will influence the situation. What are the factors that you will find here back? You will have a 1 plus Hg Lg divided by Hk Lk. And here you will have 1 divided by E. And here you will have a factor A divided by H, that I will explain in a minute, divided by m dot k Cpk. And here you have as an exponent H, which is the distance from the root of the blade. And A divided by H, H, this is the total height of the blade. So this is the integration from the root to the tip of the variable H, is equal to Hg Lg divided by 1 plus Hg Lg divided by Hk Lk. And with this parameter, we can see that if this is, let's say, a constant, there are different ways to use the equation. We see that we can increase that if we increase this, let's say, function. If Tm is a constant, if Tk up is a constant, how can I increase this? This is by decreasing the function that I have at the denominator. And you see, for example, you need to decrease that. You need to increase this, and you will need to increase this, you will need to increase that, and of course here you find again this HGLG that must be increased and HKLK that must be decreased. Of course, this is something I don't want to do, increase m dot k, but when I increase m dot k, I'm increasing Tg. What I will try to do, this is, for example, to decrease that so much that this will increase with this not increasing, but this being constant. So you see that you play with the technology in order to improve the performance of the engine at 2 levels, increasing Tg and not increasing m dot k, or not too much increasing m dot k. And the parameter that is commonly used in order to compare these different technologies and these different factors, this is what is called the cooling effectiveness. This is a sort of efficiency of the cooling. And how can we define